Hey there folks, welcome to Psych 652 Lab, module number 6. Today, as you can tell just from the title, we got a lot to cover. So we're going to talk about merging data sets, we're going to be talking about correlations, we're going to be talking about partial and semi-partial correlations, and then we're going to dig into simple linear regression. Now, first thing that I'd like to do is I'm going to have a little presentation for you actually. I wanted to give a quick note on merging data sets because there's a lot to cover with that honestly. And then also I want to try to talk to you about correlations, partial and semi-partial correlations. I remember when I was a Psych 652 student, I really had a hard time grasping the difference between partial and semi-partial correlations. So I kind of wanted to do a little brief introduction to you. Even though I know Kevin kind of covered it, I just wanted to go over it a little bit more. So let's start off with merging data sets, and then I'm going to tell you we're going to take a quick 180 after I talk about that, and we're going to talk about correlations and semi-partial correlations. So let's go and talk about joining data sets now. So I call it joining data sets. It's also merging. They're really synonymous with each other. The reason I use the word join is because of what I use is the join functions from the tidyverse, which I'm going to be teaching you today. So we're going to be joining two data sets today in R. And what I wanted to tell you is that because I just expect you in some time in your career to be joining data sets at some point, it's good to know that these exist. But really, the join function works essentially by saying, hey, what side is the data set that you honestly care most about? And what I mean by that is which data set has all the ID numbers that you mostly want. Because oftentimes when we're joining data sets, one of our data sets has like all the same IDs, and there's another data set that contains most of our IDs, but they might be missing or contains other data or other IDs that aren't existent in the left one, and it becomes this hodgepodge mess of deciding which one to do. This join function kind of says, hey, do you care most about the left data set or the right data set? Or maybe you only want the ones that merge within both of the data sets, or you only want values that you want all the values regardless of which data set they're in. And that's what this join function is doing. So the general format that our join function is going to take is, I put the star to indicate whether you do want a left, a right, an inner, or a full join to be indicated. Then you put the left data set. It can be whatever one you decide is left data set. Then you put a right data set. Again, it's kind of arbitrary. It's whichever one you choose to be left or right. And then you use this by equals and then quotation marks, whatever the name of the matching variable is in both of your data sets. So just a little note, the left join keeps all the IDs on the left data set, and you can see from this Venn diagram here. So all these are IDs that are present in the left data set, and this circle here represents IDs that are present in the right data set. And you see some of them merge together, but there's other ones that don't. A left join would drop any of the IDs that are available in the white here. And a right join does exactly the opposite of what left join does. It drops any of the IDs that are on the left data set, but not present in the right data set. Then there's also an inner join, which will only keep IDs that are available in both of the data sets. And then there's full join, which is kind of the most flexible out of all of them that says, hey, I don't care. IDs are IDs. Just give them to me. Yep. And so that's kind of the main things with these join functions. I also kind of gave this little diagram as well that shows kind of what this data set with 1 and 2 as ID numbers and 2 and 3 as ID numbers, and only 2 matches on both IDs, and it shows you what happens to the data set if you were to join these data sets together. And just so you know, there's a couple other type of join functions as well, but I didn't really go over them. There's also anti-join and I think semi-join as well, but we're not going to cover those today. But what is really important is that you know these. And something just to note, in the case that the ID numbers are exactly the same in both data sets, these all act exactly the same. So it doesn't matter whether you do an inner join, left join, right join, or full join if all the ID numbers are present in both data sets and exactly the same. So just a little cool note about that. So sometimes it may not matter which join you do if your data set is that clean, but oftentimes our data sets are not that clean, unfortunately. All right, so this is a part where I said we're going to take a quick 180, and we're going to be talking about partial and semi-partial correlations. And again, the reason I want to talk about this is because when I was in Psych 652, I found these to be incredibly hard for me to understand. I couldn't understand the difference between them, but once I got some visuals, I started really understanding. I'm going to give you some visuals of it today as well. So, partial and semi-partial correlations. What even are they? So, partial and semi-partial correlations are easily confused. Both of them are correlations that control for some third variable, and that third variable we oftentimes call a confounder. However, the way that they control for that third variable is different. So partial correlations, so imagine you have two things that are related and you want to take out the effect of a third variable from them. A partial correlation removes the part of the effect from the confounder from both the predictor and the outcome. So notice I'm talking about in the terms of predictors and outcomes here. So one variable is predicting another one, and we have a third variable that's a confounding each of them. Then there's also semi-partial correlation, where it removes the effect of the confounder from only the predictor variable. So semi-partial correlation will only take out the variance that is explained in the predictor variable. And I got a couple of images that I think are going to help explain this as well. So imagine that you have this Venn diagram here. So this is all the variance in the predictor in pink here. Then we have in green all the variance that is accounted for in the outcome here. And as you can see, both the predictor and the outcome share some of the variance explained here. So in this part right there is the part that the predictor and outcome share in their shared variance. Then we also have a confounder variable that seems to share variance with both the predictor and the outcome. In fact, a lot of variances can be explained from this confounder variable. What our job with semi-partial and partial correlations is to remove that variance that's explained by the confounder so that we can talk about what is uniquely defined between our predictor and our outcome. And in the next slide, I show how partial correlation handles it and how semi-partial correlation handles it. So I went ahead and we named the variables for you now. So our predictor variable is this variable called alc_exp, and the outcome variable is this variable called alc_gm. So in a partial correlation, as you can tell, the part from the third variable got removed from both the predictor and the outcome variable. So any variance that was explained by that confounder variable got removed from both the predictor and the outcome. Then we correlate those two variables with each other after they've been controlled for in that third variable. Additionally, there's also this semi-partial correlation. Semi-partial correlation is where it only takes away the explained effect from the confounder from the predictor variable, and then you correlate that kind of new predictor variable that has some of the effect explained taken away, and you correlate that with the complete variance of your outcome variable, so your y variable and your outcome variable. And that's the main difference between those two. And really this is going to become quite apparent, and I'll try and bring it up again when we get to multiple linear regression. Because oftentimes with multiple linear regression, we're looking at semi-partial correlations, and other times we're looking at partial correlations. So that's what's important about that. So now, without further ado, let's go ahead and start coding in R. We're going to learn about how to do partial and semi-partial correlations in R. Okay, so per usual, what we're going to do, we're going to go ahead and open up our R Studio. And we're going to go ahead and create a new project. So we go to a new directory, new project, and make sure it's saved in that correct subdirectory. And we're going to go ahead and name this module _06. Create that project. All right, so we got our project created. Now let's go ahead and get our data set. So I'm actually going to go home first here. So to find the data set, we actually have two data sets today because we're going to learn how to merge them together. So if we go to module 6 lab, we have a BAC_A and a BAC_B data set. So we're going to go ahead and download both of those data sets and make sure they're saved into the correct file path. So go ahead and just take notice of this first data set. We have an ID variable that runs 1 to about 200 observations. And we have 3 variables associated with it. Okay, so File, Save As, Browse. Go ahead and go to your my desktop, Site652, Module 06, Save. And I'm going to go ahead and exit out of that. And then we're going to go ahead and go to our BACB data set. Go ahead and download that. And notice again, this one has an ID number of 200 observations. So our IDs should match. So really, when we join these together, it's not going to matter which join we use. And we have 4 variables in this data set. So File, Save As, Browse, and then we go ahead and change it over to our desktop, Psych652, modulo 6. Go ahead and save. All right, perfect. And we can go ahead, I'm going to minimize this out. And we're going to go ahead and confirm. Yep, it looks like our BACA and BACB dataset are stored in our directory right now. All right, so per usual, let's go ahead and get our notebook running. All right, so we're going to go ahead and delete all this unnecessary text. And let's go ahead and give our notebook a title. Let's go ahead and say, correlation, partial, semi-partial correlation, and simple and linear regression. We'll just do the name SLR. So that's everything we're going to be covering in this today. And we're going to go ahead and press Enter, Tab, colon, TOC, colon, space, yes. All right, and let's go ahead and save our notebook. I'll go ahead and name it module_6_notebook. And go ahead and press save. Okay, looks like we're ready to go. Let me go ahead and pull up some notes real quick here. Okay, folks, so we got ahead and named our notebook. And per usual, the first thing we want to do is load our libraries. So we've actually got quite a few packages that we're going to be working with today. I usually try to keep it as little packages as possible, but today we're going to add on 2 new packages on top of your tidyverse and Psych. So let's go ahead and install those packages first. So let's do install.packages. And our first one is going to be ppcor for ppcore. We're going to use this package to let us get partial and semi-partial correlations. We're also going to do install.packages, and this is going to be APA, capital T, APELES, APA tables. And let's go ahead and just use the library call to call up every single library that we want. So we're going to do library, ppcore, and then we're going to do library, Psych is another package we're going to be using, library, and one of my favorite packages, the tidyverse package. And then lastly, we're going to call up that APA tables as well, APA tables. And we go ahead and let's go ahead and press play, and it's going to take a little while to load everything. So first it's installing the ppcore package. Let it do that. Perfect. Now it's installing the APA tables package. Perfect. And looks like, yep, it's loading up tidyverse. Load it up. All right. And just to confirm, yep, everything looks like it was successful. I'm going to go ahead and just hashtag these out so they don't give us any problems later. And just to kind of clear up some, there we go. Just wanted to clear up all that. It's going to go ahead and save. Okay, perfect. Okay, so today we're going to be reading in the data. So let's read in data. And let's go ahead and do insert new R chunk. Okay, so we have 2 data sets that we're going to be reading in today. So we're going to name our first one BAC_A, and we're going to use read_CSV, and we're going to do BAC_A.CSV. We're also going to do BAC_B, use our assignment operator, read_CSV, and then in quotation marks, and we BAC_B.CSV. All right, so we're going to go ahead and confirm that those works, and it looks like they're good to go. We should have 2 new objects. Yep, got 2 new objects of 200 observations in each in them. All right, so this is where we're going to go ahead and join our data sets together. And let's go ahead and just take a look at our data sets real quick. All right, so looking at BACA, so we have our ID numbers, our weight, tip drinks, and alk XP. And then in BACB, again, we have the ID number that's associated. That's what we're going to be matching on. P mood, absorbed, alk GM, and BAC. So let's go ahead and type in hashtag join, and I'll put in parentheses merge our data sets. And let's go and create a new R chunk. So because all of our IDs match in this case, it doesn't matter which join we work. They're all going to work exactly the same. I'm just going to go ahead and do it with the left join, just because usually I like to do left joins. I don't know why. I just conceptually understand it the most. Sometimes I'll do an inner join where I'm only getting cases that are in both of them. But in this case, we're just going to go ahead and do a left join. So what we're going to do is we're going to name a new object. I'm going to name it BAC underscore joined. And then I'm going to use an assignment operator to save it into a new object. Then we're going to use the function left underscore join. Then we do our left data set. I'm going to say BAC underscore A is the left data set, comma, and then our right data set, which is BAC underscore B. Then we do comma, and then we say by equals, and in quotation marks, it's whatever the matching ID variable is. In our case, it just so happens to be also called ID. But just in your, if you ever had a different variable, sometimes it could be ID with capital I and a D, or something like that. I work with mentees and mentors, so sometimes it's called mentee ID or mentor ID. But essentially what you need to do is make sure you have at least one matching variable. So if we run this line of code, we're going to have a new object called BAC joined with 8 variables in it. So let's go ahead and check. Yep, we have 200 observations of 8 variables. So it didn't drop any cases, but it added new columns. So the reason it didn't go to 9 variables is because we kept that ID variable exactly the same. We joined on that ID variable. So we have ID, weight, tip drinks, AlkX, P mood, absorb, AlkGM, and BAC new variables, which is great. So we have a new join data set. So in the future, if you ever want to join data sets, left join, right join, inner join, and full join are really the ways that you want to go. So per usual, I know we just made this data set bigger by joining it, but I'm just going to go ahead and reduce it right now so that it makes it a little bit easier for us to work with. So let's go ahead and name it select variables of interest. Okay, so we're going to go ahead and insert a new R chunk, and we're going to name this BAC underscore reduced. Go ahead and create an assignment operator so that it's a new data set here. And we're going to do the select function. Name our data set, which is BAC underscore joined, comma. And the only variables of interest for today are going to be weight, alk underscore GM, which is the grams of alcohol consumed, and then BAC, which is their blood alcohol content at the end of the night. Just for a little bit of information on what our variables that we're working with today are going to be. So let's go and do that, and if it's correct, it should run. Yep, okay, so we have BAC reduced, which only has 3 variables. I didn't even include the ID variable. We don't need it today. But weight, alk GM, and BAC. Okay, so now we've done that. Let's go ahead and describe the data. So we're going to use the psych package describe to do this. So describe the data. Today we're going to be using psych packages describe to describe our data set. We won't be using the summary function. Describe gives us a little bit more information, especially great for when we have continuous variables. So BAC underscore reduced, just to get a good understanding of what our variables are like. All right, so again, we have 3 variables, weight, alk GM, and BAC. There's 200 observations in each of them. The mean of our weight is 68. I don't know if that's kilograms or pounds, honestly. I believe, yeah, I'm not sure. Then we have alk GM. It's probably kilograms. We have the grams of alcohol consumed in a night, and then the average BAC level as well, so blood alcohol content level. So it's good just to get a little good feel of what our variables look like. Looks like the skew and kurtosis are okay on them too. Okay, so we went ahead and described our variables. So now I want to go ahead and make a scatter plot, and I'm particularly interested in this alk_gm variable and BAC. I want to see how many grams of alcohol you consume in a night is related to your blood alcohol content. As we know, I would guess that those are pretty highly correlated, but let's go ahead and plot the actual thing. So let's go ahead and write a new header and say make a scatter plot. Okay, so we're going to go ahead and make a scatter plot. So we're going to use ggplot. So for use ggplot, we start off. First thing we need is our data set, BAC_reduced, comma. Then we need our aesthetics, and think about it. What does a scatter plot need? It needs an x and a y-axis. So our x-axis is going to be alk_gm. So we're going to use alk_gm to explain our y variable, which is BAC. So we've got our aesthetic function set in there. We do plus. We're going to use geom_point, parentheses. And we're going to go ahead and do something called adding a regression line in there too. We're going to use a function called geom_smooth. So we add it as a new layer. So this is going on top of the geom point. So it'll be literally right on top. It's just another image stacked on top. And we're going to use this thing, an argument in there called method equals, and in quotation marks, LM. And what that's going to do is going to add the best fit linear line to your graph. So let's go ahead and do that. And it should create, there we go. So we have alk_gm on our x-axis, BAC on our y-axis, and as you can see, it's a pretty clear linear trend, given a little bit of error here, but it seems like as people drink more throughout the night, have more grams of alcohol consumed in the night, the higher their BAC level is. So we even have someone, a world record holder over here at 0.15. They had a lot of grams of alcohol and they have a 0.15 BAC. Remember, 0.08 is kind of the legal limit for driving, so that's around here somewhere. So keep that in mind. Okay, so the next thing I want to do is I'm going to teach you how to get the correlation of a data set, and then I'm also going to teach you a really great way for outputting APA-style tables for correlation matrices as well. And this is really cool. When we get to the apa.cor.table part where we're creating APA tables, it might blow your mind. It blows my mind that we're able to do this. But we can create correlation tables that are just ready for publication access. But let's go ahead and do it first the simple way. So let's go ahead and create a new header called get correlation of variables. Okay, and we're going to create a new second level header actually called via core function. Okay, so we're going to go and insert a new R chunk here. So really, what we're going to do is we're going to use this core function, so COR, and all you need for the core function is to enter in your data set, so BAC_reduce, and this is where it comes in advantageous to minimize our data set as much as possible, because if we didn't do this, we'd have this large correlational matrix that we don't really need all the variables for. So we're going to go ahead and do this core BAC_reduce, and it's just going to correlate all of the variables in our data set. So we have weight, alk_gm, and BAC that are going to be correlated with each other. So go ahead and press play. All right, so what we have here are now correlations. So notice that it's a new matrix here, and everything, and it's symmetrical as well. So 0.12 is the same up here because it's correlating things with each other twice actually throughout this matrix. So you really just want to focus on one side of this. And additionally, we have these 1.00s just indicating that its weight is correlating with itself. But what we can see is that our main kind of correlation of interest is this alk_gm and this BAC. So it seems like there's a 0.86 correlation, which is a really big correlation. Remember, correlations go from -1 to +1, with 1 representing a stronger relationship in that correlation and 0 representing no correlation. So we have a pretty high correlation between alk_gm and BAC. So, and we can kind of see that from our graph as well. It's like, wow, okay, that's a pretty good correlation. Okay. Now I'm going to do something that I think might blow some people's minds. We're going to do something called create. Let's see. We're going to do a second level header, and it's going to be via apa.cor.table. And this is going to be really cool. What it's going to do is create an APA-styled table for you that you're able to just smack right into a manuscript if you'd like. So let's go ahead and do this. So what we do is the function is apa.core. Oops, don't know why that showed up. apa.core.table. Okay, I'm getting some errors here. And we're going to go ahead and use this function called we're going to name our data set BAC reduced, comma. So the first thing it takes is your data set. Then what we're going to do is in quotation marks, we're going to name what we're going to have a new file path. So what this is going to do is going to create a new Word document in the project folder that you created. That's going to be a perfectly APA styled correlation table. I know it doesn't make much sense now, but what you're going to do is type in BAC underscore reduced dot doc. That's saying you want it to be saved as a .doc, which is pretty much a Word document. Then we're going to do show.conf.interval equals true. So that means that we're setting it so that it'll show us confidence intervals as well. All right, so this doesn't look like anything now, but it's going to be really cool what happens here. So the first thing we're going to do is we're going to go ahead and press play. Okay, so it shows us some output here. So it shows us this output, and what it did is it showed us it gives us all of our variables, the mean, the standard deviation, and then also the correlations that we saw before. And it also indicates where those values are significant with stars. So it looks like this correlation of BAC and LGM are significant, and additionally the correlation between BAC and weight is significant as well. It seems like there's a negative correlation, which would make sense. As weight goes up, your BAC would be expected to go down. And you see that our mean of BAC was 0.08, and if we scroll up to our describe function, there it is, 0.08. So that got the correct thing. Now, you'll notice in your project file, something called BAC underscore reduced.doc showed up. Additionally, if we scroll over to module 06, we have a new BAC underscore reduced Word document that showed up. Go ahead and double click on that document. And it'll show up eventually. Showed up on my other screen, that's why. And voila, this is a APA formatted table for you. All you need to do is change what the number of the table is and the variable name so that there's something that make more sense. And then you can go ahead and copy and paste this into your APA manuscript, because I know all of you are going to be writing manuscripts pretty soon. So I think that's really cool. It is a total time saver. I don't know if you've ever tried to create an APA table correlation matrix in a Word document before, but it is a pain. This does it all for you. So it's really great that we have this available. So go ahead and exit out of that. I just am geeking out over that, so just let me have my time and do that, and then we can go ahead and move on. Okay, so now that we've gotten all that out of the way, let's go ahead and do something called, let's go ahead and get those partial and semi-partial correlations. So let's do this. So we're going to go ahead and do two hashtags, and we're going to say get partial correlation. Now, normally I try to keep you within this tidyverse realm where I try to make it so that we don't have to dig into data sets with $sign operators. Unfortunately, we're going into a time where we can't do this and we have to go with base R functionality. So we're going to be using two functions. One of them is called pcore.test and the other one's called spcore.test. And what these are going to do is they're going to be able to give us the ability to get partial and semi-partial correlations respectively. But before we get started on those, I'm going to go ahead and do $pcore.test. I don't know why that error keeps showing up. I'm sorry about that. And we're going to go ahead and press enter. Must have something to do with my internet. I don't know what's going on. Jeez. Hold on one second. Okay, that was a waste of time. Hey there, students. Sorry for the delay there, or the break in the video, but I was experiencing some problems with R. So as you can see, even I experience problems with R's every now and then. But I want to go ahead and get back to what we were talking about with partial correlations. So I'm going to go ahead and I'm going to type in the name of the function. Let me go ahead and load up my notes again. And it's going to be $pcore.test, because I want to show you something about this so that we can know for future use what's going on. So we got the help document. So we have this function called apa.cor.test. It takes an x, a y, and a z, and it already sets a method for us. However, x, y, and z are what we need. It's called a numeric vector. So whenever you see this in a code, that means that you're working in base R. And what we're going to have to do, unfortunately, is we're going to have to tell R to dig into our data sets and find the variables that we want. So let's go ahead and write a note here. Say, we are going to get a partial correlation where we are going to correlate, it's going to be alk GM and BAC, comma, while controlling for weight, period. So we're going to go ahead and do this. So we're going to do pcor.test. Now, remember, these call for a numeric vector. So we're going to do x equals to indicate what our x is, x equals, and then we're going to do BAC underscore reduced, which is the name of our data set. Then we're going to do a $sign operator, and you'll notice R is pretty smart and already knows that we're trying to dig into our data set. And we're going to first do alk GM, so go ahead and do alk GM. So what this is saying is, I want you to go into my BAC reduced data set and pull out the alk GM variable. Then comma, we're going to do y equals BAC underscore reduced, then a $sign operator. Then we're going to do BAC. So what we're saying is we want to correlate x and y. We want to correlate alk GM and BAC. And then this last one, z, and we want to say while controlling for BAC reduced, we want to control for weight. So if we go ahead and do this, and again, the only reason we have to do this is because this function requires 3 numeric vectors to work, as opposed to using just where you indicate the data set or something like that, like this apa.cor.table did. If we run this, we're going to go ahead and get a partial correlation. And voila. So our partial correlation is 0.9565, so pretty large correlation. And what that's saying is the relationship between BAC reduced and the relationship between alk GM and BAC is 0.956 after controlling for weight. So we're going to control for weight, then we're going to correlate these two. So that's a significant p-value, and it says that it got all of our observations, and it says that it used the Pearson method, which is exactly the method that we want to do. Now, we're going to do another one. We're going to get the semi-partial correlation. Now remember, that partial correlation took away the variance control that was being explained by weight from both the predictor and the outcome variable. In the semi-partial correlation, we're going to be doing it where it's only going to be taking away the variance from the predictor variable. So this function, and if we do !spcor.test, we're going to go ahead and run that. And it looks exactly the same. So this requires 3 numeric vectors. In fact, this is really going to look just like our pcor.test. So we're going to do spcor.test. Then we're going to do BAC underscore reduced, $sign, alk GM. And we can go ahead and signify that. You don't need them here, but we're going to go ahead and do them anyways. But we're going to do x equals. We're going to fill in those arguments. We're going to do y equals. Then it's going to be BAC underscore reduced, $sign. This is going to be BAC, comma, z equals BAC reduced, $sign, and this is going to be weight. So if we do this, this spcor.test is going to give us the semi-partial correlation. So go ahead and press run on that. And as we see, the semi-partial correlation is 0.94. And if you'll notice, it's a little bit lower. So like I said, I'm pretty sure most of the time at least, when you do this, your semi-partial correlation is going to be lower than your partial correlation because that correlation, it has all of the variance of y to correlate with. Whereas with partial correlation, there's less to correlate with each other, so it gets up more power to get a higher correlation. So what this is saying is that I took out this this weight variable from the alk GM, which is our x variable, and then correlated it with all of the variance of y, is what it's saying. Okay, so that's it for the correlations aspect of it. We're going to actually go ahead and start doing a simple linear regression now. And all a simple linear regression is really, we're just looking up, we're just going to be finding the slope of this line essentially. And you're going to go ahead and see what's going to happen when we do that. Okay, so let's go ahead and create a new header called get fit. Sorry, it's going to be fit a simple linear regression. We're going to put SLR model. And with this model, let's go ahead and say we are going to predict BAC using AlkGM. So we're going to predict BAC using AlkGM, and we'll show you how to do that. So let's go up and go ahead and create a new R chunk. All right, and go ahead and do this. So what we're going to do is we're first going to create an object. I'm going to name this object mod1. And then I'm going to go ahead and use an assignment operator. Then to the right of that, we use a function called lm. And then in parentheses, we go ahead and indicate what our model is. So what our model is we're going to first say we want to predict BAC. So we're going to do BAC. Then you create a tilde, and if you're confused where that tilde is, it's shift and it's the button right above tab on your keyboard. It'll be a squiggly line that comes out. We're saying we want BAC to be regressed on alk_GM. So in this case, this is AlkGM predicting BAC. Then we do comma and say data equals BAC_reduced. And that's all you need for this model. So this is going to be taken in 2 steps. So first step, we can go ahead and write first step, specify model and save it into a new object called mod1. So I'm going to go ahead and scroll this down, so we're going to see what happens. So in here, you're going to have a new object called mod1 that's going to show up. Perfect. We have a new object called mod1. If you click on this, it has a lot of this information, but we don't know how to access this information. We want coefficients, we want the F value, we want a lot of different things, but it's all in here, but we don't know how to access it. It's kind of hard to look into. We have our coefficients there. We're going to use the summary function in order to display this model. So the way that we do that is so let's go ahead and write, we can go and just write, we don't need it. Let's go ahead and do hashtag display the model. And I'll go ahead and write below, we will be displaying our regression model with the summary function. So you've used that summary function before. This summary function can work in a lot of capabilities actually. So we go ahead and do summary, and then we do mod1. It's whatever the name of that object you named is, so mod1. And we go ahead and press play on this, and voila, we have a summary of our model, of our regression model. So there's a lot of information on here, and I'm going to point out the things that are the most interesting. You kind of have to read this out of order. First, what you want to read is this F statistic and P value right here. This indicates that what our model was significant and what the F statistic was. So we had 1 degree of freedom and 198 degrees of freedom, so 1 and 198. Our P value is 2.2 to the -16. So notice it's in scientific notation. So this is a quote unquote really significant model. I don't really like using that term, but the model is significant with an F statistics of 597.5. So what it's saying is there's something statistically significant about AlkGM explaining BAC. It seems to be doing a really good job at it. We also have our R² value that we want to look at. That's 75. What this value means is that 75% of the variance in our BAC variable can be explained by the AlkGM variable. So it's explaining 75% of the variance in blood alcohol content. Then we can additionally look at our intercept and our AlkGM. What this intercept is saying is when AlkGM is at 0, our expected BAC is let's see, it's 0.003. So the expected blood alcohol content of someone who has had 0 grams of alcohol throughout the night is 0.003. So basically 0. And that's to be expected as well. Additionally, this AlkGM says for every 1 unit increase in AlkGM, the expected rise in blood alcohol content is 0.002. Notice how it's in scientific notation. And that's significant at a p less than 0.05. So what we're saying is that I'm going to rephrase that again. For every 1 unit increase in alcohol and grams of alcohol consumed, we expect to see a 0.002 increase in somebody's blood alcohol content. And that makes sense, right? When someone drinks 1 gram of alcohol, their blood alcohol content would go up. And that's really all you need to know about simple linear regression. If simple linear regression is confusing to you, please come into lab and we can talk about it. And I'm going to go ahead and plot. I'm actually going to go ahead and copy this code from up above here, just so we can kind of visualize what's going on in this regression model. So let's go ahead and write plot the regression model, and you'll notice it's exactly the same model we did. So we're using alcohol GM on the x-axis and BAC on the y-axis. So what we're saying is that this line has a slope of 0.002. So every 1 unit increase in AlkGM, we get a 0.002 increase in our line. And it kind of may not look that way, but think about the way that this is scaled. So 0.002. So every 1 unit increase over here is associated with a 0.002 increase here. Additionally, if we were to have this line run all the way so that it was at 0, and I can actually show you how to do that as well. We would have this line run all the way to 0 on the y-axis, so it would keep going and keep going and keep going until this AlkGM hit 0. We would hit the y-axis at exactly 0.003. And we can actually go ahead and plot that right now if we wanted to. I'm going to go ahead and copy and paste some code because I know if I do it by myself while I'm talking to you, I'm going to mess it up. But I'm going to go ahead and paste some code. And you can go ahead and copy down this code if you want. Just pause the video and try and copy it down. It's a lot to do, but just to kind of show you what's going on, what I've done is I've done the ggplot, x-axis is my AlkGM, y is my BAC, done a geom point. I added in a layer of a geom smooth with a method equals elm. I also did this thing called full range equals true, which essentially is going to continue this line so that it continues down even if it doesn't have data. I set some x and y limits here. I am going to add some other lines just to clarify some points later, and I annotated it to indicate where the intercept is. So we're going to go and press play on this. And just a note, so notice how with ggplot, all I'm doing is adding in more and more plus signs, and I'm just layering one thing on top of the other. That's all ggplot is. You can add as many things as you want if you just keep using these plus signs and making sure they map onto things correctly. But let's go ahead and press play, and voila. So what I'm trying to show you here is that our intercept is 0.003. So if we let this line from earlier extend all the way out towards it hits the y-axis, or it will hit the y-axis at 0.003. So again, someone with a 0 alcohol GM, so someone who has grams of alcohol consumed of 0, is an expected blood alcohol content of 0.003. I mean, you would expect it to be 0 because they had 0 grams of alcohol, but it's a prediction, but it's a pretty darn close prediction to 0 if you got it right. And yeah, so that pretty much sums up everything about the simple linear regression. So just to kind of confirm what we did today. So we loaded up a few packages. The new ones were the pp.core package, which is for the partial and semi-partial correlations. The apa.tables one is the one that gives us those really nice correlation tables. And you're familiar with Psych and Tidyverse. We learned how to merge data today. We did the BACA and BACB, and then we merged them together with one line of code. Then we reduced the data set. Then we described our data set. Then we just plotted what it would look like, and we ended up using that plot again later. Then we got the correlation, and you can see how easy it is to correlate variables with each other. And additionally, we used this really awesome apa.cor.table, which created that cool Word document for you that you can make APA tables. And then we used the pcor and spcor.test, and we learned how to use this kind of $ operator for the first time to dig into our data set. So this is probably one of the few times that I'll actually be requiring you to use these, but they're really good to know. You unfortunately can't get away from base R sometimes, but you know what? Learning base R is a great thing. I was originally taught on base R, and I feel like I'm all the better programmer because of it. And then what we did is we started fitting a linear regression model. We went over what the linear regression models are. If you have any questions with that, please don't hesitate to ask me. And then we plotted it. So let's go ahead and just yeah, so that's it for the lesson today. I'm going to go ahead and check on my time. Okay, and then what I'm going to do is let's go ahead and just download those data sets for the assignment. So what I have for you is a assignment where I'm going to be asking you to merge in two data sets. Then I'm asking you to get the partial and semi-partial correlations, as well as run a simple linear regression model. So go ahead and look at that activity that's available for you on Module 6. And you have two data sets available as well. And additionally, I also have a, I guess I don't have a variable descriptions for you. I'm sorry about that. But either way, I think you may have used the weight loss data set before anyways. But either way, okay, well, good luck on your assignment. Let me know if you have any questions. Thank you so much.